You ever wonder why a massive AI, one with, hundreds of billions of parameters, can sometimes feel like it has the memory of a goldfish? Well, it's this really fundamental, kind of weird inefficiency in how even our most powerful models handle basic knowledge. Okay, let's dive into this, because a new approach is trying to fix it for good.
I mean, really think about it for a second. Every single time you bring up a common phrase or a famous person, the model has to burn a huge amount of processing power just to reconstruct that idea from scratch. It's kind of like having to rederive the laws of physics every time you want to drop a pencil. Yeah, it works, but man, is it incredibly wasteful.
So here's the big picture. On one hand, you've got today's models, which are basically faking memory through sheer brute force computation. But on the other hand, we have this new idea. What if we just gave them a real, dedicated memory? A system where they can look up a fact instantly, what the tech folks call a constant time or O of 1 lookup, and it doesn't matter how big that memory gets.
So here's what we're going to cover in this explainer. First, we'll break down this memory problem in LLMs. Then we'll introduce this new concept, a new axis of efficiency called memory. We'll look at how a system called Engram actually makes it work, check out its really surprising results, and then dig into why it makes models deeper, faster, and way better with long contexts. And finally, we'll think about what this means for the future of sparse AI.
All right, so let's get right into the heart of the issue. This incredible waste of AI brainpower on stuff that should be super simple.
And this quote from the source paper just hits the nail on the head. Our current models are using their deep, complex, powerful networks for what is, at the end of the day, a glorified table lookup. It's like using a supercomputer to do basic arithmetic. Sure, it gets the job done, but it's not very smart.
This table just lays it all out so clearly. Recognizing a simple entity like Diana, Princess of Wales, isn't just one step. As you can see there in that first row, the model has to use multiple heavy-duty network layers to slowly piece that concept together. Every step just chews through processing power, what we call floating point operations, or flops.
So, this all brings us to the solution. And it's not about throwing out all that powerful computation we've built. Not at all. It's about adding something new to the mix, a whole new axis of efficiency. Memory.
The official name for this is conditional memory. Now, you've probably heard of mixture of experts or MoE models. They're super efficient because they only turn on parts of the AI's brain for any given task. Well, conditional memory is a totally different kind of efficiency. Instead of activating just parts of the brain, it just looks up pre-stored facts, which frees up the entire computational brain to focus on what it's actually good at. Complex reasoning and creativity.
Okay, so how do you actually build this thing? Well, the implementation is a module they call Engram. And what it does is it takes a classic idea from way back in language processing and gives it a serious modern upgrade.
Engram has this really elegant two-step process that just makes sense. First, it retrieves. It sees short patterns of words, these are called engrams, hashes them into an ID, and then pulls a matching entry from this huge memory bank. It's like your brain spotting a familiar phrase. Then second, it fuses. A really smart context-aware gate looks at that memory it just pulled up and decides, hey, how relevant is this to what I'm thinking about right now? And then it blends it in.
But what's really clever is how Engram brings this old Engram idea into the 21st century. It uses tokenizer compression, so it knows Apple and Apple are basically the same thing. It uses multiple hash functions to avoid memory collisions, getting the wrong entry. And that context-aware gate is like a bouncer, making sure only relevant memories get in. It's a whole suite of smart upgrades that make the system actually work in the real world.
Okay, so the theory is elegant. It's clean. But does it actually work? Well, the results are where things get really, really surprising, because the benefits go way beyond just having a better memory.
So the researchers posed this fascinating question, which they called the sparsity allocation problem. Basically, if you have a limited budget to make a model efficient, how much of that budget should you spend on the computational experts, the MoE part, versus how much you spend on this new memory system?
And what they discovered was this distinct U-shaped relationship, which you can see right here. Go all in on just computation and your error rate, your loss, is higher. Go all in on just memory, and it also struggles. The magic, it turns out, is right there in the middle. The hybrid model that balances both, it gets the absolute lowest loss. It seems computation is inefficient without memory, but memory can't replace computation.
And they even found the sweet spot. The best models were the ones that dedicated about 20 to 25% of their efficiency budget to this new Engram memory system. That's huge.
It suggests a real, practical design principle for building the next generation of AI.
Now, here is where it gets absolutely wild. You'd think a memory module helps with, well, memorizing stuff. But the biggest performance gains were in general reasoning, a massive 5-point jump on the really tough Big Bench hard benchmark. And it wasn't a one-off. The same thing happened in a totally different area, coding. The Engram model got a 3-point boost on the human eval benchmark. This isn't just about remembering facts anymore. It's about freeing up the model to think better. And the improvements were just incredibly broad, right across the board. Just look at this list. Knowledge tasks in English and Chinese, scientific reasoning, math problems, the hybrid Engram model consistently beat its twin even when they had the exact same computational cost.
So what is happening here? Why does adding a simple lookup memory suddenly make an AI model better at reasoning and coding? Let's get into the mechanics of why Engram is so dang effective.
This chart, a CKA map, is the whole key. It looks complicated, but it tells a really simple story. See how that bright diagonal line is shifted up and to the left? That's telling us that an early layer in the Engram model, let's say layer 5 on the bottom, is already thinking as deeply as a much later layer, like layer 12 in the regular model. By offloading memory, Engram makes the entire network effectively deeper without adding a single bit of computational cost.
And this effective depth has these massive downstream benefits, especially when you're dealing with long documents. Because Engram handles all the local, common phrases with memory lookups, it frees up the model's really precious attention mechanism to focus on the big picture, on long-range connections. And the result? A huge leap in accuracy on those needle-in-a-haystack tests, from about 84% all the way up to 97%.
And the system design itself is just incredibly slick. Because the memory lookups are predictable, the system can prefetch the data it needs from cheap, abundant computer memory, while the super powerful GPU is busy doing other things. This means you can have a gigantic 100 billion entry memory table with almost no performance hit. It's just smart engineering.
So what does this all add up to? What does it mean for the future? Well, we could be looking at a truly fundamental new building block for artificial intelligence.
The authors themselves conclude that conditional memory is likely to become an indispensable modeling primitive for next-generation sparse models. That is a powerful statement. It suggests we're moving away from a world of just pure computational scaling towards a more balanced, smarter, hybrid approach.
And this really leaves us with one final, big thought. For years, the race in AI has all been about scale, about raw power. But maybe, just maybe, the true path forward isn't just about building bigger and bigger models, but about building smarter ones. So is the future of AI not just about being more powerful, but about being fundamentally and beautifully more efficient?